Hello and welcome back to the lecture of time series econometrics. In this lecture, we are specifically going to deal with the covariance structure that we see in AR1 process. All right. Now, for AR1 process, we normally represent it as something like this. Where I write yt equal to phi yt minus 1 plus epsilon t. Now, if I'll do some little bit of mathematical manipulation here to kind of come to the covariance structure of the AR1 process. So let me write yt, let me extend a period, and I will write this equal to phi yt plus epsilon t, right? Epsilon t plus 1, right? And similarly, if I write yt plus 2, I will write phi is yt plus epsilon t plus 1, and then of course I will have my this period error term, which is epsilon t plus 2, right? Now look at it carefully. So what I'm trying to do is I'm actually going to express y2 plus yt plus some h or whatever I want to put here in terms of yt, because when I do the covariance structure, I need to get the covariance between yt plus h and yt. So that is why precisely I am following this way of derivation. Okay, so let us just do a little bit of more sort of expansion to this, and I'll write this yt, then I'll write phi et plus 1, and then I'll write et plus 2. Okay, let me reduce the size a bit here. In the same fashion, I can write yt plus 3 is equal to, I will use the same notations where I want to actually keep the yt on the right hand side, right? So I will use a value of yt plus 2, which means, I will write it again, phi square yt, and then I have my phi et plus 1, and then I write et plus 2. Now of course I have my this period et plus 3, right? 70 plus 3. Now if I expand it, what I get here is phi cube yt phi square et plus 1, and I have my phi et plus 2, and of course the last term is et plus 3. Now you see the pattern here. The general pattern that you can see is you can simply the number of period that you increase, you can basically get that order of phi, and of course you can multiply with yt, so it is not changing, so you can simply keep it as it is, right? So if I write like that, what I will get, if I say have something like a t plus h period, so what I will be able to write is, let me use a different color for that because it's important line that I'm going to write. Okay, so let me write y t plus h. So the first term is going to be phi power h and yt. Okay, what about the error term? So you're getting a series of error values, right? So how that series is actually distributed? So if you see, it is basically if I have 3, then it's starting from 2, right? So, and it is going up to 0, phi power 0, the last coefficient. So basically the value of phi is going to be distributed from 0 to, t plus h minus 1 if I'm considering t plus h periods, right? So I equal to 0 to t plus h minus 1, and of course the value of rho, the power of rho is going to be t plus h minus sorry, not row, phi operator here, sorry, t plus, I can write basically, I can, on the other side, I can just write I, right? So phi I, and here my error term epsilon is going to assume values from what? From again t plus, so basically the last term it is going to take, which is basically t plus h, that value it is going to take, right? So that would mean I have to, if I write t plus, say, t plus h minus I, so that means if I'm starting I from 0, then I think we're all good, right? So t plus, the last term is going to be t plus ith value is t plus h minus 1, so which you subtract, so you'll have only error for the first bit. So that's perfectly fine. So that is basically going to be the value of the yt plus h. So that's basically the most important part. And now we are going to see the covariance structure considering the yt and yt plus h. Okay, so let me just write it down here. Cov, let me use a different color here. Cov yt plus h and yt. If I expand that, cov yt plus h is going to be yt plus I equals 0 t plus h minus 1 phi I e epsilon h minus I. So that's my yt plus h, comma, my simple yt, right? Now if I expand it, so you see I can get two terms here, yt and the first term, phi power h yt, and the error term. Now the error term, if I separate these things out, that is going to be 0, because the yt and the error terms, they're independent, and each of this error term, if I take the expectation, they're all going to be 0, right? So what I'll have the left, the first term here, the phi power h yt square, right? Now that the covariance of yt with yt is nothing but the variance of yt. So what I can write, it is basically going to be variance of yt, and what will happen to the phi operator? It will simply come out, right? Simply come out, right? Now, what is the variance in case of a AR1 process? So we have seen that previously. The variance for AR1 process is nothing but, so if this is my phi operator, the variance is going to be sigma square by 1 minus phi square. So that's the value, that's the variance we have for a stationary AR1 process, right? So that value we are going to use. So that is basically the covariance term that we are going to get for the AR1 process. So we get all the properties of AR1, and we are ready to compare the properties of AR1 with any other processes that we are going to see.